Welcome to FASTA-QC2 presentation. Let me introduce myself. My name is Sabah Goma. I third year medical informatics student, Mansour University. This is a project for genomics course. This video will see the mobile app version with Flutter technology. If you have an account, click on login. If you don't have an account, click on sign up and create account. Moving the next screen, upload file. After uploading the file, the next step features. The application has a lot of features. The first feature, basic statistic. It appears in the form of a table. Pair-based sequence quality. It appears graphically. Pair-based sequence quality scores. Pair-based sequence content. Pair-based GC content. Pair sequence GC content. Pair-based in content. Sequence length distribution. Duplicate sequences. Overrepresented sequences. Overrepresented keywords. We are done and Jamila will present the final project, a desktop version.
Assalamu alaikum wa rahmatullahi wa barakatuh. Hi, in this video I will show you how to run FASTA-QC2 app. First, you have to open CMD in the folder that has all files of your app. You can run FASTA-QC2 app by executing this command, Python followed by FASTA-QC2.py. FASTA-QC2 app consists of many features. The first feature is basic statistics, provides many things: file name, file type, total sequences, maximum read length, minimum read length, total lengths, joining and cytosine percentage content, and sequences that have no gaps. I will try with a file, so the first thing is to enter file path of this file. I will try with this file. You can see result of this analysis by pressing these buttons. Other features are implemented independent of each other. By this way, you have full control on features. You can do analysis by executing exactly one feature, two features, or any number of features that you want. And by this way, you can do analysis on different files at the same time. In this video, I will try to execute all these features on only one file. To execute any feature, you have to write this command, Python followed by the file name of this feature. I will start with duplicate sequences feature. This feature takes two files, file path of the file that has all reads, and the second file is adapter file to see that if by mistake the sequencing machine made sequencing to adapter on adapter. Then I will execute overrepresented keywords feature by the same way, Python followed by the file name of this feature. then overrepresent the sequences by the same way. This feature also takes two files. First file is the FastAQ file, and the second file is the adapter file. Then I will execute the pair base GC content. Then pair base and content. Then pair base quality scores. Then pair base sequence content. Then pair sequence GC content. Then pair sequence quality scores. And finally, sequence length distribution. You can see result of this analysis by executing Python followed by fastaqc2.py. Pair base sequence quality, press here. As we see, y-axis provides quality scores across all bases. X-axis provides position in red. The blue line is the mean of quality scores across all bases. Pair sequence quality scores, press here. As we see, y-axis provides a number of repetitions. X-axis provides thread score. Pair base sequence content. Y-axis provides frequency, and x-axis provides position in red. Pair base GC content, press here. Y-axis provides frequency, x-axis provides position in red. Pair sequence GC content, press here. Y-axis provides frequency, x-axis provides mean of GC content across all sequences. Pair base and content, press here. As we see that most of reds have no gaps. Y-axis provides frequency, x-axis provides position in red. Sequence length distribution, press here. Y-axis provides frequency, x-axis provides sequence length. Duplicate sequences, press here. Y-axis provides frequency, x-axis provides sequence duplication level. Overrepresented sequences, press here. As we see that these are sequences that are overrepresented. Okay, the first sequence is this sequence is overrepresented for 103 times. Overrepresented keyers, these are most overrepresented keyers across all reds. Y-axis provides frequency, x-axis provides position in red. Thank you for watching.
بسم الله الرحمن الرحيم. انا بلال عماد، قسم بايو انفورماتكس فرقه ثالثه. دلوقتي هنشرح فكره مشروع ماده الجينومكس. المشروع عباره عن MSA موبايل ابلكيشن. MSA اختصارا لمالتيبل سيكونس الاينمنت. الابلكيشن ان شاء الله يكون استخدام سهل وبسيط. احنا صممنا الابلكيشن بلغه دارت وفلاتر فريم ورك. تمام. طبعا انا خلاص ده الكود وبشغل الكود كده بيظهر لي. ده اول حاجه دي الشاشه بتاعه الابلكيشن. تمام. ده بعد السبلاش سكرين. بيظهر لي كده بيقول لي اللي هو دخل اول حاجه دخل نوع الانبوت بتاعي اللي هو نوع السيكونس يعني، فاختار اللي هو DNA. المفروض كده هو مستني ان انا ادخل له سيكونس من نوع DNA. هنا طبعا ده السيكونسز، ده المربع ده اللي بدخل فيه السيكونسز. هنا ده بدخل فيه الماتش، وده الميس ماتش والجاب اللي هو الماتش سكور والميس ماتش سكور والجاب سكور. تمام. بعد كده لو اجرب كده ادخل له سيكونس غير، يعني سيكونس فيه حرف غير حروف DNA، وليكن مثلا ACTG. تمام. وادخل حرف مختلف، ادخل يو مثلا UCTG. تمام. وادخل له ATCG تاني، واجرب كده ان انا اشغل جيت اوتبوت. طبعا طلع لي اللي هو بيقول لي دخل فاليد انبوت لان ده انفاليد. ليه انفاليد؟ لان انا عندي حرف من حروف مش من حروف الDNA اللي هو اليو. تمام. فاجرب كده بقى ادخل حرف عادي وليكن A مثلا، كده المفروض يبقى فاليد عادي. بس دي ACTG يعني خليها CTG عشان يبقى كلهم ايه شبه بعض، عشان نشوف هيعمل ايه لما يكونوا كلهم ماتشنج مع بعض. تمام. جيت اوتبوت طلع لي ايه السيميلاريتي سكور ب 20. ليه ب 20؟ لان انا هندخل له قيم ديفولت، هندخل له قيم ديفولت مكان الماتش والميس ماتش والجاب. لو انا ما دخلتهاش يعني، فهو البرنامج بيدي قيم ديفولت. الماتش ب5 والميس ماتش ب-5. تمام. فانا لما عملت له جيت اوتبوت المفروض كلهم ماتش مع بعض، فهيطلع ب 20. ليه؟ لان انا عندي الماتش ب5 في 5 في 4 ب 20. تمام. حاجه ثانيه، نجرب كده ندخل قيم كلها مختلفه، كلها مس ماتش مع بعض. ندخل مثلا 4A وندخل 4C و 4G. زي ما قلت هو مس ماتش ب-5. تمام. فهنشوف كده طلع لي ايه؟ طلع لي -20. -20 ليه؟ -5 في 4 ب-20. تمام. نجرب احنا ندخله قيم من عندنا. طبعا لما ندخله قيم للماتش والمس ماتش والجاب هو يبدا يتجاهل القيم الديفولت اللي كان واخدها. تمام. فادخله انا قيم من عندي، مثلا ادخله 2 للماتش و-2 للمس ماتش و-1 للجاب. تمام. هنشوف كده هيطلع لي ايه. طلع لي -8. -8 ليه؟ لان -2 في 4 اللي هم الاربع حروف دول يبقى -8. تمام. هجرب كده بقى انا ادخل له قيم من عندي، ادخل له حروف عشوائي بشكل عشوائي. تمام. وليكن كده مثلا طبعا مش لازم يكونوا قد بعض يعني، عادي. نشوف كده هيطلع لي الاوتبوت ايه. طلع لي كده الاوتبوت في الشكل ده، تمام. والسيميلاريتي سكور طلع ب 53، تمام. ده كده الماتشنج ما بينهم. طيب بعد كده هبدا ان انا نجرب كده مثلا نشغل الابلكيشن على الموبايل، تمام. ده كده الشكل الابلكيشن على الموبايل اهو، تمام. طبعا ظهر الاول عندي السبلاش سكرين، وبعد كده دي الهوم سكرين بتاعتي، تمام. نفس الكلام هنا بقى، تمام. كده وضحنا فكره الابلكيشن بتاعنا.
السلام عليكم، معاكم آية صلاح من كلية الحاسبات والمعلومات جامعة المنصورة، قسم ميديكال انفورماتكس، مادة الجينومكس، تحت إشراف دكتورة سارة المتولي. فكرة المشروع بتاعي أنا وزمايلي خلود وهناء وأسماء وريهان هي ويب سايت بقدر من خلاله إني أعمل ألاينمنت عن طريق إني بدخل تو فايلز. أول فايل هو الفايل فاستا وده الخاص بالريفرنس، تاني فايل هو فايل فاستا كيو وده الخاص بالسيكونس. بستخدم في الالاينمنت الجوريزم هو الجوريزم البورز ويلر، والالجوريزم ده عندي فكرته سريعا ان الكود بيتقسم ل3 اجزاء. اول جزء هو الخاص بالبارسنج للداتا، وهو اني بقدر ان انا اقرا الفايلات اللي انا بدخلها للويب سايت. اول حاجه بيقرا عندي فايل الفاستا كيو، تاني فايل بقراه هو فايل الفاستا. تاني مرحله من الكود هو ان انا بعمل اندكسنج، وده عن طريق 3 methods الموجودة عندي. تالت مرحلة من الكود بيبتدي في مرحلة الsuffix array، والsuffix array بتخزن فيها الsuffixes اللي هو يعني بيبدأ من عند البوزيشن رقم كام في التكست. بعد كده بيبتدي في مرحلة البري بروسيسنج. البري بروسيسنج بيعمل فيها أو بستنتج منها الكاونت تيبل والاوكيرنس تيبل. بعد كده بيبتدي في مرحلة الالاينمنت نفسها، وفي مرحلة الالاينمنت احنا استخدمنا الجوريزم بوير مور هوريزون علشان يقدر يعمل لي مالتيبل باترن، بس في الحالة دي احنا طبقناها بس على الاكزاكت ماتش. بعد كده بيبتدي في مرحلة ال FM index iteration. في مرحلة ال FM index iteration كل مرة بيجيب interval بيدور فيها على الريد أو الباترن الموجودة عندي، ويعرض لو هي موجودة بيعرضها هي موجودة بنسبة كام في المية. بعد كده بيبتدي في مرحلة الباكورد سيرش. الباكورد سيرش بيمشي على الباترن أو الريد ويعمل كذا FM iteration علشان يوصل في النهاية إنه يجيب المينيمم ريشو فيما فوق. يعني مثلا لو أنا دخلت 50% هو هيجيب لي من بداية ال50% فيما فوق. بعد كده بيبتدي في مرحلة ال inexact search، ودي هنشوف النتيجة مع دلوقتي، ودي بعد كده الهيدرز، وبرضه هنشوف النتيجة. أول لما بنفتح الويب سايت بتاعنا بتفتح لي الصفحة بتاعة إن ندخل البيانات بتاعتي. أول حاجة بيطلبها مني هو إن يدخل المينيمم سكور، وليكن مثلا إحنا هندخل 60%. في هنا صلاحية إني أدخل التكست أو السيكونس اللي أنا محتاج أعمل عليه alignment، ولكن هي حتى الآن مش شغالة. فالبديل إن إحنا نرفع الفايلات اللي إحنا هنعمل عليها alignment. فأنا حالا هعمل upload لفايل الفاستا كيو، وهعمل upload لفايل الفاستا الخاص بالريفرنس، وهنستنى الفايلات تحمل، وبعد كده تظهر لنا النتيجة بتاعتي. النتيجة اللي بتظهر أول حاجة بتظهر لي هي نتيجة الإكزاكت ماتش. الإكزاكت ماتش عندي بيعرض أول الريد ده موجود في البوزيشن رقم كام جوه الريفرنس فايل، فهو هنا موجود عندي في البوزيشن رقم 37. الريد التاني موجود في البوزيشن 5148، وهكذا في الريدز الموجودة عندي في الفايل. تاني جزء بيعرضه هو الهيدرز. التو هيدرز دول هما الموجودين أو اللي احنا قدرنا نطبعهم من السام حتى الآن. دول خاصين اول حاجه، اول هيدر موجود عندي جوه الاس ان التاج. ده الهيدر الموجود او الخاص او اللي اتقرأ بالفايل الفاستا. تاني هيدر عندي، تاني تاج موجود عندي ال ان، وده اللي بيبقى مسؤول عن ان هو يطبع لي طول الريفرنس بتاعي. تاني هيدر عندي هو البي جي، وده الخاص بالابلكيشن اللي انا شغاله عليه. اول حاجه في الاي دي بيبقى موجود اسم الابلكيشن نفسه، والفي ان بيبقى موجود الفيرجن. بعد كده بيعرض لي نتيجه الالاينمنت نفسها. بدايه من هنا عندي الستارت بوزيشن، ودي بدات اعمل او ادور على من اول البوزيشن رقم كام. فهنا عند 5356، وبعد كده بدأ يطلع لي نتيجة الماتش ريشو، وهنا 61%. هو دلوقتي الباترن بتاعي ظهر في أكتر من مكان جوه الريفرنس فايل، ولكن احنا حتى الآن بنعرض أفضل ماتشنج سكور طلع عندي من الأماكن اللي ظهرت جوه الريفرنس فايل. آخر حاجة بيعرضها هي السفكس أري، والسفكس أري اللي بدأت اللي موجودة عندي أو اللي بدأت أعمل من عندها الألاينمنت، وهكذا في بقية الريدز الموجودة عندي حتى آخر نهاية الفايل. ده اللي قدرنا نوصل ليه حتى الآن في البروجكت. إن شاء الله نحسنه بحيث إن السرعة تزيد، وكذلك يبقى فيه فيتشرز أكتر.
Hello everyone, this is Sarah Hamad, student at Faculty of Computer and Information Science, Medical Informatics Department, and this is a descriptive video for our project Pattern Behind Chaos, made in the Genomic course. Okay. First of all, the front end. The front end of our project has two pages. The first page leads to the main page. In the main page, you are expected to enter some data. Format of your data, is it FASTA or FASTA-Q? Type of your data, DNA or protein, and if the data is already in your local machine, upload the file. If not, just provide the link for it. The number of chimers and size of chimers. You could think of number of chimers like how many times should I run this code for the same data. Like if I enter 2, I expect to have 2 outputs, okay, and so on. Size of chimers, you are just providing the value for the chimers you just say. Okay, now, what are chimers? Chimers are substring of length k in a given string. Okay, you could think of chimers as a k character. You are taking a k character, okay, as a substring of the whole string. Like if I would like to take a trimmer, okay, ACG is a trimmer, AGG a trimmer, TAC a trimmer, and so on. Okay, CGA, is it a trimmer? It is. GAG, it is. AGG, it is. So, how can I construct all the possible trimmers for this DNA sequence? Okay, first of all, I will take the first G character, ACG, then exclude the first character and add up a new character. Okay, like ACG, then CGA, GAG, AGG, and so on. And there's a rule telling you how many chimers will you get, like length of the sequence or length of the string. And here, as you can see, these are 11 characters, and if I would like to construct affirmers, well, the rule says L minus K plus 1. L length of character, K is like the integer you are providing, or the length of each substring, plus 1. So 11 minus 4 plus 1 would lead to 8. Okay, these are all the possible formers for this DNA sequence. What our project actually does, it constructs all the formers. If you said your chimer size is 4, it constructs all the formers, then provide, like by doing some calculation, it provides its probabilities, and constructing these probabilities in a matrix. This matrix or like this matrix then is turned into an image. Okay, so this is the output, an image holding the probabilities of each chimer. Okay, these are the two photos for the same data. This is part of the matrix, okay, probabilities, and this is the image after like converting it into an image. You're converting this matrix into an image. You can see there is pattern. Darker regions, lighter ones. Lighter ones are having greater values, darker regions having less values, and so on. Okay, Rolling a die is governed by probabilities, but yet it has a pattern. Also, the process may seem random. What does that mean? Okay, let's say I have a die and I'm rolling my die. Okay, so if I get 1 or 3, I will do some action. Okay, 2 or 4, I will do another action. 5 or 6, I'll do totally different action, and so on. Okay, let's say this is my initial position. If I get 1 or 3 after I rolled my die, I will start like moving towards this point. Okay, this is my initial position. I will start moving towards this point. Like, okay, this is my initial position. Okay, if I get 1 or 3, I'll start moving to this point. Okay, I already have the coordinates of my initial position. Already know the coordinates of this point and this point and this point. So, calculating the distance, dividing by 2, this would be my new point. And by keeping this process, I will end up with some pattern like that. Okay, some pattern. And as you can see, the yellow pattern is the same as the red one, is the same as the blue one, because all of these are representing like the probabilities in here. As you can see, each die has 1/6 probability for occurrence, and each point is holding 2 values, right? Okay, now same idea would be applied for DNA bits. Okay, rather than a triangle, we would represent a square, and rather than like the numbers, we would represent the bases, something like that. This is a square, and each corner is holding a base. Okay, let's say this is my initial position, and the next base is T. So I already have these coordinates, measuring the distance, dividing by 2, I would end up in here. And then if the G is the second base, like doing the same process, I would get some pattern. Okay, this project is based on chaos game representation, and you could read about it in here, like if you follow this link. Okay. If you follow this link, you would be able to read more about this idea. Okay, now, is it possible to do the same thing with protein? Well, protein have 20 amino acids, so we would like construct a polygon with 20 corners. That would take a lot of coding, a lot of calculations. It's overheading. So what about turning protein back to DNA? Okay, it's like a shortcut, but it's not accurate, and it's not like correct, totally correct. It's not wrong and not right, because you could have one amino acid and several triplet codons may lead to this amino acid. Which one would you pick? And actually we would argue, if you're treating all your protein data with the same rule, you're getting a rough idea about how the correct data should be. Okay, so we constructed a reverse translation table. Okay, reverse translation table. And in this table, we say the first triplet codon that could have occurred or could have caused this amino acid is taken as the right triplet codon. Okay, well, it's not accurate, but let's say I made a project that gives me 2 values, 4 and 2, and the expected ones are 3 and 1. Well, values are not the same, but the relationship between them, it's right. Like 4 minus 2 is 2, 3 minus 1 is 2. So it's giving you a rough idea about how the right answer should look like. Okay, now this tool could show you the pattern in different genes. Okay, either in the same species or different species, same species, okay, or among different species, so on. Okay, now let's run the code. Okay, let's run the code. F for file, U for URL. Okay, I will enter F, a file, and it's DNA.FASTA. It's a DNA file, it's FASTA file. We would like to represent one camera, its size is 6. So case game representation for 6 Mars. Okay. And, URL. Okay, U. And this is, I already have my link in here. Okay. So this is my protein link. If you have a weak internet, it may take some time. Okay, now it's protein, it's FASTA sync. I'd like to present 2 cameras. The first one is 4. Okay, as you can see, this case game representation for 4 cameras for the protein given by URL. In second camera, let's say we'd like to present a high one, 19. It's too big. So case game representation is 4 cameras also. As the size of the camera is too big or too small, the camera is set to default value of 4. Okay, F for protein, I have P_FASTA. Okay, it's FASTA. Okay, let's try FASTA-Q. I have a FASTA-Q now. Okay, FASTA-Q. Okay, it's protein. Okay, it's FASTA-Q. How many cameras you would like to represent? 1. 3 more. Okay. Already my data are not like the FASTA and FASTA-Q are not whole data. They are just smalls already filled with comments. They're describing each part of it. So I hope you would understand it easily. This project was made under Dr. Sarah El-Metwally observation, and the team members are Asma Ayman, Samir Rifai, Carlos Magdi, Mohammed Nasif, and me. And thank you for your time.
Hello everyone. In this video, I'll explain briefly what the package is and how to use it. And I'm gonna also explain some use cases where you can actually use the package to build something on your own, or maybe use it in your own projects. Well, first of all, this package is just an API wrapper around the UCSC Genomic Restful API. Well, first of all, let's dive in UCSC and see what it actually offers, and then we're gonna see what we actually accomplished here to make it easier to integrate the UCSC Genomic Restful API in your own projects. Well, first of all, the UCSC, we all know that it's genome browser. It gives you ability to view tracks and genomes on your own machine, maybe online or your local machine. It also offers you the ability to retrieve the data and use it in your own projects, maybe in your own genome browser. So to fully understand this, we just have to take a look at the 2020 paper released by the UCSC Genome Browser. It manually releases a paper that illustrates everything that is new in the UCSC Genome Browser and offers more and more convenient ways to access and retrieve the data. So one of the ways was Restful API. It's stated here that previously users who wanted to download a track or sequence data would need to grab the data set in its entirety. It means that you have to take all the data in the database servers on the UCSC to use it, maybe to use, let's say, 1,000 track or something. And of course, that was not dynamic at all. Maybe some analysts who just need to grab, let's say, 1,000 regions or something, as stated here. So they have created a RESTful API that returns JSON formatted data for variety of data retrieval queries. So to recap all the paper, UCSC gives you endpoints that you can call the endpoints with some optional and required parameters to get some specific data. This endpoints ranges from getting a list of public hubs, getting a list of database genomes, to the rest of the endpoints. Of course, all these endpoints are now implemented in our package, and it's time to move on to our package. Now, after we saw the endpoints and we know how to deal with the endpoints, you're gonna have to call the endpoints and get you some JSON formatted data that you have to parse it to a Python object. Then you're gonna have to, on the Python object, you're gonna have to do some operations or method on it. And let's say that you want to do some kind of getting tracks of a genome. So all this gonna be pain, still gonna be pain, because you still have to know all the request library to make the HTTP request and then parse the response to a Python object, then call the Python object to call methods on. This is an overhead, and your code can be messy in a very short time. And here came our project to solve this problem, and it offers an expressive API and an easy to use API to handle all that requests for you. You don't have to do any kind of HTTP request or any parsing at all. All you have to do is to call a function on a given class name, and here all of your data is ready for you as Python object. Let's see. All you have to do to get a list of all hubs available is to import hub at first, of course, and then call the get method on the hub. And it will return for you a list of all the public hubs in the UCSC genome browser. Of course, that stands for everything else. You're gonna have to do some kind of functionality like hub.find. You have to find a specific hub. Maybe you have to do some kind of operation on the hub. You have to find the hub, maybe to search for a genome or something. Let's say that you want to find the hub by something else rather than the name, or rather than the URL. You can get any attribute from the hub. Of course, I'm saying attributes because the hub here is a Python object. It has an attribute. You can use any of the attributes available to find the hub by the attribute name or by attribute value. Of course, that you have to find, and then you have to print. This is just an overview. Of course, the documentation is long enough to get everything, of course, in the track section. But we're gonna see some kind of how to use the package, and of course, the documentation will illustrate everything else. Okay, so of course, the package is now available at PyPy here, so you can install it via pip easily. Like this, pip install UCSC Genomic API is the first release, is 1.0. Here I'm gonna use a collab just to clarify things more. Here I'm gonna install the package and hopefully it will work. Let's see. Take some time. Yeah. Collecting and downloading. Requirement already satisfied. Successfully installed. And this is good news for us. So after we installed the package, we can actually use it right now. So how can we use it? Well, first of all, what is the endpoint that you want to use? Let's say that you want to get all the genome browser database genomes. Let's say that you want to get all the genomes available. All you have to do is to import the genome, then call the get method on the genome class. Okay, it will return to you a genomes list. You can loop over it to see the output of the method. So let's do something like this. Just copy and paste for saving time. It will not return any response, but it's now all saved in the genomes list. So if we loop over the genomes list, let's see, and to print, let's say the genome name. Okay, the genome name. Well, first let's make it a text so we can see all the objects in here. And here all the genomes in the UCSC database as Python objects, which means that we all have to do just to access something like the source name, for example. Let's see, source, any attribute to return the source name of each genome in the genome database. Of course, this is only one endpoint. There are tons of endpoints left to try. It depends on your use case. If you want to track data, if you want a specific sequence, let's say that you want this sequence. Where here. So let's say that you want a sequence. This sequence, of course, belongs to a specific genome on a specific chromosome. All you have to do is to import sequence at top and then call the get method on the sequence with the required genome and the required chrom. Of course, you may add optional parameters such as start or end. Okay, so now let's try this. Let's see how it works. Well, first of all, I want to print the sequence. Here I import the sequence, then I call the get method on the sequence with the required parameters, okay? Of course, you can change this to anything that you like, as long as it's genome at the UCSC database. So let's print the sequence and see how it goes. And of course, it returns a sequence object. So if I done something like this, the DNA, and I want the sequence itself, and it will return the sequence itself. Of course, there are if you return the dect, of course, you can see the object and its attributes at the end and the start, if it's belong to a track, if it belongs to a hub, if it's belong to a chrome, the DNA itself, and I think there is still in a genome. I think that can be modified a little bit just to get the genome at first. Okay, so anyways, all these attributes, of course, you can call it. Maybe you will be interested in DNA to get the DNA itself, and it is done. Of course, you can get anything that you want as well. If you want some specific tracks, if you want to build your own genome browser, if you want to analyze some specific tracks, this package will be of great help to you. Okay, now that we know how to use the package, it's time to see how things work under the hood. Okay. Now, if we go to the folder UCSC, and if you go to api.py, of course, all the code lives in api.py, and it is just to tell Python that this is a Python package, and this is just for testing, and this is just for testing. So api.py is our goal here. Okay. So now let's dive in the code under the hood and see if I can, get the outlines clear and how the code works or how the code flow works. If you want to extend the package later, this part of the video will help you indeed. So the package was divided into some classes, okay? Each class, a member of the team was working on it. As you can see here, there's a class for hubs, there's a class for genome, there's a class for sequence, and it goes on. What I want to point out here is that each entity in the genome or in the hub or the UCSC genome database represent a class here in the package. That's why it provides an expressive API to use, because you can call the get method on the genome itself, not an endpoint. Things will be much clearer in the code. As you write the code, you want to focus more on the things that you want to implement, rather than just calling an endpoint here or return or parse an object here. So as I stated in the documentation, there's primary classes such as hub, which have, of course, this is constructor to construct the attributes. Here it takes a variable number of attributes and set the attributes, the name and hub URL, long label, and so on. Here's a get method, as we tried in the demo, to get a list of all the genomes in the specific hub. Find, if you want to find a specific hub by the hub name, if you want to find by a certain attribute. Let's say that you want to find the hub by URL, okay? Now you can use the find by. And of course, there is a code reuse for hub in hub.get that I'm calling the method get in here, and I'm looping over it. I'm getting the attribute value of this object, then I'm gonna compare it with the value. If it's found, I'm gonna say that it's found, and I'm gonna return the hub object. I don't want to get too much in the details in here, but I just want to show you the workflow of our code. What we have done in the hub, we repeated it in the genome, of course, with a different implementation, with the different endpoints in here. Just the same idea, but a different class names or different entities. Of course, you're gonna find something here is gonna also be useful for you, is raise exception of request, which means that if you tried to look for something that does not exist, it will raise an exception and tell you it does not exist. It does not crash in your program or something. So let's try to run this. It will not work because it will tell you that you can't find the genome. Of course, that also depends on the two classes defined here, not found exception, not allowed exception, because I'm saying that when the status code is 400 or 403, return that something went wrong or the requested resource is not allowed to be accessed. Okay, so it's gonna also be tolerate any error that you make in the code. If you misspelled a genome name, it's gonna tolerate this, and so on. Okay, so I think that's everything that I wanted to say about the package. Of course, I imported a request here, request library, and it's downloaded via pip if you install the package. So if you try to install the package here, you will find that requests will be installed throughout in the process. Okay, and just for a little note here that in the middle of the video I paused the video to push a new release because I found some bugs. So I just finished the demo. Thank you all for listening. And I just want to point out that this package was a part of a project to a subject called Genomics under the supervision of Dr. El-Metwally in 2021, Mansoura University, Faculty of Computer and Science. And I want to also clarify that I was just the presenter to the video, but I was a part of a 5-member team. And I want to thank them all for their efforts. They made all the heavy work. They made all the brainstorming and meetings and pushing comments and all. So thank you. I want to thank them all. And I want also thank anyone who would like to contribute to the package, or maybe even give it a star. Maybe give some advices or some information, something to maybe get better in the future. And I would also like to thank Dr. Sarah especially for her outstanding efforts and for encouraging us to do such a package. And I really don't think any of this package would have been possible without her informative courses, especially in genomics and bioinformatics. I will leave the link below if you want to know more about this. It is on GitHub as well. And I recommend the course to anyone interested in bioinformatics or any related fields. So thank you all for listening, and have a nice day.
السلام عليكم ورحمة الله. أتمنى حضراتكم جميعا تكونوا بخير. معاكم زينب العزب، طالبة بقسم ميديكال انفورماتكس المستوى الثالث. ده مشروع لمادة الجينومكس تحت إشراف دكتور El-Metwally. احنا مجموعة من الطلاب عملنا فلاتر اب للبلاست ان. وأول حاجة هنبدأ نشوف الابليكيشن بتاعنا. دي هنا الهوم فيها معلومات عن البلاست بشكل عام، وهنا الليرن مور هيبقى معلومات عن البلاست ان، لأن الابليكيشن ده متخصص في البلاست ان. طب تمام، اهم حاجه علينا هو جزء السيرش. هنبدا نعمل سيرش. اول حاجه لو انا عايزه اعمل الاينمنت بين 2 سيكونس، اول حاجه انا هدخل السيكونس الاولاني وهدخل السيكونس الثاني. وهختار هنا نسبه السيميلاريتي اللي انا عايزاها. انا اخترت هاي سيميلاريتي، انا محتاجه يكون نسبه السيميلاريتي عاليه، وهبدأ أعمل بلاست عشان يجيب لي نتيجة السيرش. هنا جاب لي نتيجة السيميلاريتي بيرسنت، وجاب لي الألاين الأولاني والألاين التاني، وجاب لي الأوتبوت بتاعي. تمام. وفي اوبشنز تاني لو أنا عايزة أختار فايل. هنا لو أنا عايزة أعمل السيرش ما بين فايل أنا هختار من عندي مثلا دوت فاستا مع الداتابيس بتاعتي أو مع فايل تاني. خلاص أنا هختار الفايل اللي أنا محتاجاه. مثلا انا عايزه اعمل كويري، تمام، على الفايل ده اعمل اوبن، وبرضه بحدد نسبه السيميلاريتي وبضغط على بلاست عشان تجيب لي نسبه السيميلاريتي. نيجي هنا بقى لنتيجه السيرش. اول حاجه دي اسم الوتر مين سكور، السكور بتاعي ده هيكون السكور بت، وده هيكون اسم الفايل الموجود في الداتابيز، وده الاندكس اللي موجود اللي بدأ عنده اول ماتش، وده الجزء اللي حصل ليه ماتش وموجود ان هو ماتش ات مع ده هيكون اسم الداتا اللي موجود عندي في الفايل اللي انا اخترته عشان اعمل عليه كويري. وبعد كده دي اكستنت هاي سكورنج، اعلى سكورنج حصل الاتش اس بي هاي سكورنج بير مع الجزء ده. ويبدأ يعمل كده مع كل الفايل بتاعنا. هيبقى هيدينا دايما اسم ووتر من سكور، السكور بتاعي في الجزء ده، وانا لقيته فين، حصل هيت فين في الداتابيز، اسم الداتابيز، والجزء اللي حصل ليه هيت، واللي حصل ماتش مع اكتر حاجه لها سكور اللي هي HSP. تمام. نبدأ بقى نروح للكود. اهم حاجه عندنا وهي جزء الكود. احنا مستخدمين بايثون كباك اند، واستخدمنا فلاتر كفرونت اند. تمام. بايثون عندنا اول حاجه ده جزء المين، ده فايل المين، ومستخدمين فلاسك عشان نعرض جزء الاوتبوت. اول حاجه انا هيبقى عندي الفايل اللي انا اخترته ده هيكون امتداد فاصله، فانا محتاجه اعمله فورمات عشان اقدر اعمل عليه السيرش. اول حاجه انا هبدا اعمل فورمات للداتا بتاعتي، الكويري داتا والداتابيز بتاعتي، عشان اقدر اعمل عليهم السيرش. وعندي فايل اسمه بريبير ده الفايل اللي هيعمل ليها فورمات للداتا، بحيث ان الاوتبوت بتاعها في الاخر هيكون على هيئه ديكشنري. تمام. هعمل سبليت والاوتبوت بتاعه هيكون ديكشنري عشان اعرف اعمل سيرش. تمام. خلاص انا عملت كويري. بعد كده انا هبدا استدعي داله السميث ووتر من وجزء الفلتر منها. تمام. داله السميث ووتر من انا بيبقى عندي في الاول داله هحسب منها السكور الاينمنت. خلاص حسبت السكور الاينمنت، هبدا اعمل ماتريكس امليها بقيم السكور الاينمنت اللي انا حسبتها. تمام. وطبعا معروف عن دايما بنقل قيمه 0، وبعد كده الليفت سكور والاب سكور والدايجونال سكور. وبعد كده بحسب الماكس سكور، اعلى قيمه عندي في الماتريكس بتاعتي. بعد كده ببدا اجيب الالاين الاولاني والالاين الثاني وبعمل لهم انفيرس. بعد كده الاوتبوت بتاعي ان انا بملي الاوتبوت بتاعي، بحسب الاول نسبه السيميلاريتي بيرسنت. احنا هنا كان كل ما الكاركتر هيكون متساوي هيزود نسبه السيميلاريتي بواحد. خلاص هتبقى السيميلاريتي بيرسنت على لين طول الالاين بتاعي 100. خلاص كده انا حسبت السيميلاريتي بيرسنت. ودي دالة هتعمل فلتر عندي اللي هتحذف السيكونس لو هو اقل من السكور بتاعه منخفض جدا. تمام. بعد كده هيبقى عندي جزء الفلتر. انا هعمل فلتر للورد اللي اقل من الثريشولد، وبرده ليها كود عندي هيكون جزء الفايل ده هيعمل ووردز السكور بتاعها فوق الثريشولد، مش هضيفها للفلتر ليست بتاعتي. يبقى هي مهمتها ان الالجوريثم ده هيحذف الكلمات اللي اقل من الثريشولد بتاعي اهو. الجوريزم اون فورمات الداتا هيشتغل طبعا على الفورمات الداتا بعد ما بقت في شكل الديكشنري، وهيعمل ريموف للوردز اللي اقل من السكور ثريشولد. بعد كده انا هروح احسب الاكزاكت ماتش اللي حصل فيها ماتش فعلا. هيجيب find all exact matches of every filtered data. انا برضو اشتغلت على الفلترد داتا اللي بقت هنا اقل من الثريشولد بتاعي، والاوتبوت بتاعها هيبقى على هيئه ديكشنري. خلاص جبت الاكزاكت ماتش، وبرضو ليها كود. هي في الاخر خالص الاكزاكت ماتش دي هترجع لي اسم الداتا نيم اللي موجود في الداتابيز، والماتشز دي هيكون فيها الكويري بتاعت الورد اللي انا عايزه اعمل عنها استعلام، والمؤشر بتاعها في الداتابيز، والمؤشر بتاعها الاندكس بتاعها في الكويري، الفايل بتاع الكويري. تمام. خلاص رجعت الاكزاكت ماتش. هيكون عندي بعد كده الادجيسنت بير ده هياخد من الانبوت ذات نفسه الداتا اللي انا هدخلها له، هيكون على هيئه ديكشنري، وهيديني البير فلترد. هياخد hold both words from the pair و how long they are، طولهم قد ايه، هيجيب اللينس بتاعها و where they both هو موجودين فين في الداتابيز والكويري بتاعي. بعد كده هعمل اكستنتد البيرز دي اللي هجيب من خلالها ال HSP، اكتر هاي سكورينج بيرز، اكتر بيرز حصل لهم سكور. الفايل بتاعها طبعا الاكستند اهو. تمام. هتاخد عندي الاكستند بير اند وير ات از فاوند، وهي موجوده فين في الداتابيز، واعلى سكور، صاحبه اعلى سكور عندي. طبعا بعد كده هيعمل صورة الاكستنت بير، هيرتبهم عشان يعرض الاوتبوت بتاعي. خلاص هنا قلنا طبعا انا استخدمت ال HSP عشان احسب السكور بت. ده هيكون السكور بت بتاعي، هطبعه عند اسمها ووتر مين سكور، هيكون ده السكور بت. وهيت ات انا لقيته فين، هيبقى مكتوب طبعا اسم الداتابيز، الداتا نيم اللي انا لقيتها فيها، وهيكون موجود جنبها المؤشر بتاعها هي موجوده فين في الاندكس. وكمان دي هتبقى الداتا ذات نفسها، جزء السيكونس اللي حصل ليه الاينمنت هيحصل له ماتش ات، ده هيبقى اسم الفايل اللي انا عملت له، اللي انا عايزه اعمل له كويري اصلا. واكستنت اد دي هيبقى جزء الداتا اللي حصل لها اكستنت زي ما انا لقيت هنا، زي ما القدران هنا، ده البيت سكور بتاعي. وهيت اد حصل له هيت اد، ده اسم الداتابيز بتاعتي، والاندكس اللي هو بدأ عندها السكورنج، وده الكود اللي حصل له سكور، اللي حصل له ماتش سوري او الاينمنت. وماتش اد ده اسم الداتا اللي موجوده عندي في الكويري فايل اللي انا عملت له سيلكت. وبعد كده الاتش اس بي سكورنج، القيمه اللي حصل لها اكتر حاجه حصل ليها سكور. كده نكون قدمنا فكره مبسطه عن البروجكت بتاعنا. شكرا.
Hi everyone, Khalid Gad is here, and today I'm gonna introduce our brand new tool which called Super Aligner. So let's get started. First, what is sequence alignment? Sequence alignment is the process of comparing and detecting similarities between biological sequences. This helps us to identify regions of similarity that may be a consequence of functional, structural, or evolutionary relationships between the sequences. Now we need how many types of alignment. Actually, there are only two types of alignment. First, pairwise alignment, which is only between two sequences, and multiple alignment for three or more sequences. By using more than one algorithm to build up a tool that combines the pairwise and multiple alignment algorithms in one place to make the alignment easier. And that's how our aligner tool come to life. So let's test it up. First, let me show you the manual of the tool and how to use it. As we can see here, here's a bunch of options we can use with the tool. Here's -H for help, it will bring the manual as we can see here. -Q for quality chart, it will display the sequence quality score chart. And -Q score chart for display the rate of gaps, mismatch, and match between the result of sequence. -T for translator, and it will translate the DNA sequence to a corresponding protein. -S for Smith-Waterman algorithm, and this algorithm is for local pairwise alignment. -N for Needleman-Wunsch algorithm, and that's for global pairwise alignment. -B for progressive, and -I for iterative, and both of these are for multiple sequence alignment. And -F here if you want to provide the sequence in a file in FASTA-Q or FASTA file, and we just need to enter the path of the file here. -S if we want to provide a sequence by hand, and -Q to give a corresponding a quality of a corresponding sequence. Now let's start testing the tool, and we will start with the -N for global alignment. But before that, I should mention that some of these options are mandatory, like we must specify the algorithm that we will use, and we must specify the method that we will use to provide the sequence. So let's start with -N. Here, -N for Needleman-Wunsch algorithm, and I will provide the sequence in a FASTA-Q file. So I will write -F, and I will give the path of the file. Press enter, and as we can see, here's the result of the two lead or two sequence. Let's take a look of this file here. We have the first sequence here, and we have the second sequence here, and here's the global sequence alignment between these two sequences. Now let's Now let's provide the -q option and -g option and see what will happen. As we can see here, it gives us the score quality, a chart of score quality of the sequence, and it gives us the rate of gap and mismatch and match. He tells us that we had 10 gaps for mismatch and about 70 matches. Now let's provide -t and see what happened. And here it gives us the corresponding protein of each sequence of this. Now let's test the -s for Smith-Waterman algorithm for local alignment, and I will provide the sequence by hand just like this. I'll provide the same sequence in the file, so I will take it as a copy paste here. First sequence, and here the second sequence. Press enter, and as we can see, here is a local alignment between these two sequences. Now let's test the multiple sequence alignment, and we will start with -b for progressive alignment. We will provide the file which contains the sequences, and here. It's in FASTA file, and press enter, and here is the multiple sequence alignment between the sequences in the file. Sorry for that. If we enter -i, it will give us the result of iterative alignment of these sequences. And if we can look at this file here, here is the file that contains the sequences that we do the multiple alignment to it. Now that's a super alignment tool, and finally, because of what happened this semester, our tool is under development and it's not ready for production yet. Thank you.